Yes, hello, this is Stefan. Let's assume we have a noisy input analog signal and we would like to get a nice clean output signal. We have to do some filtering on top of this input signal. And we could do that with a digital filter, but first of all we have to have some sort of a digital representation of that signal. Otherwise we can't do any computation. And so we do sample this signal with an analog digital converter, take at time discrete time steps samples of this signal, convert it in a stream of sampled digital information, and use these data points within a digital filter, do the computation on them, add them up, sum them up, multiply them with coefficients, divide them, and then sum them back together, and then you have an output representation of digital data points. And this stream of data points is then fed into a digital to analog converter, and that's converting back your digital representation of the output into an analog signal. There are a few important things you have always to take into account when working with digital filters, and that's mainly you always have to fulfill the Nyquist criteria. The sampling theorem says that your sampling rate, at what frequency you sample this input signal, has to be at least twice as fast as the highest frequency of interest. And if you don't do that, if you have frequency components on the input that do not fulfill Nyquist criteria, then you will get all kind of nasty mirrored and mixed signals here, and false interpretation of your input signal. So to make sure that we always fulfill Nyquist criteria, we put a low-pass filter at the input, a so-called anti-aliasing filter. And this anti-aliasing filtering is just reducing the bandwidth of your input signal to the limit of your Nyquist, so that your Nyquist criteria will always be met. Here on the right side, I've designed a digital filter. I'm using this IIR or this FIR filter designer from Iowa Hills again. It's free to download. I have a link down below. And this filter here is a very performant, very steep filter. It has cutoff at 1 kilohertz. It has almost no ripple at 0.002 decibel ripple at the passband, really flat and then really steep roll off. And a super performing filter. It has to have 129 taps. We take a look at that later. 129 coefficients, quite a bit of computing power to calculate the filter like that digitally. If you want to implement a filter like this in the analog world, it's going to be very difficult. I would say it's probably not possible. I've taken here a 6-pole filter, analog filter, CL. And you have a significantly higher ripple in the passband. You don't have such a high and steep roll-off. You could also use active filters, 3 stages probably of Sallen-Key topologies in a row, and you would probably still not get this wonderful performance here on this digital, like on the digital filter. The digital filter also has, the FIR filter at least, has a linear phase response, which is very nice for high fidelity applications, high quality audio applications. And of course you have no dependency on component tolerances, which you always have here on these analog filters. And tight tolerances on capacitors is very difficult and very expensive. And also in the digital world, you can change the filter parameters on the fly. While you're running your application, you can change according to your needs on the fly. Your filter performance, you can shift the corner frequency from 1 kilohertz to 2 kilohertz if you want to, and do all kind of stuff and change your filter performances. And you try to do this in the analog world. All right, maybe the scope of digital filters is very wide. You could say that the minimum or the simplest digital filter I've seen so far is a moving average filter. The highest sophisticated kind of filter is fast Fourier transformation. The moving average filter is very simple. You take samples. In this case, we have 5 samples, a current sample and the last 4. We take these 5 samples, we multiply each sample with 0.2 and then sum them up. So we sum up 5 samples, each sample with the same coefficient multiplied, and then that's my output. And then for the next sample, I just take the last 4 again plus the actual, the new sample, and sum them up again, and then put it the result to the output. Very simple. We've all probably done that before. The FIR filter is exactly the same actually, except that it's taking different coefficients. It's not only 0.2, so you have to do more computation here. And we saw before this high performance low pass filter I've designed there has 129 taps. That means it uses 129 sampled data to generate the output. So it takes computation power, really. That's FIR, finite impulse response. And IIR filters we talk about in a minute. The difference from FIR, IIR to FIR is that you also take the output and feed it back into the calculation. We take a look at that in a second. And then, of course, fast Fourier transformation. That's a method, an algorithm, how to do discrete Fourier transformation on a sampling, on sampled data, like we have here. We take the same sampled data and we do DFT on it, and then we get as output information the frequency components that are in this signal and at what amplitude they are represented in this signal. So if you want, so it's somewhat related to digital filters. All right, the two main filters we see all the time is, as we mentioned already, this FIR and this IIR. And really the name of the filter says it all. FIR means finite impulse response. If you have an input signal, let's say 1 volt, and you drop it to 0, and then you monitor, the output will be eventually 0. If you do this with the infinite impulse response filter, the output will never ever get really to 0, theoretically. And that's because you don't only use the input, and actually if you look at the input side, the calculation of the input side, it's exactly like an FIR filter, but you also have a computation of the output, the history of the output fed back into the summation of the filter. And therefore, if you have an input and you drop the input back to 0, you always feed back a little bit of the last output. And even if that's getting really small and really small and really small, you never get to 0. So, nice thing about FIR, we already learned, has a linear phase. It's always stable, easy to design, and some say even, some say you have to have more computations needed. However, on the IIR, it has a nonlinear phase response. It might have a ripple in the passband and the stopband. It's potentially unstable. And other people also say this is more representing, an IIR is more representing an analog filter world. And, we know the problems of stability there. So it's the same thing here. And maybe you need fewer computations. But if you need more or fewer computations for FIR and IIR, it's really dependent also on your hardware. Do you have a floating point unit? Is your microcontroller supporting you with digital signal processing or not? And what are the computing speeds for multiplication and divisions? And a lot of things like that. And also, of course, you have to compare approximately the same filter performance. You cannot just count the taps and then make the comparison. You have to compare the performance and then make the comparison of speed. But yes, computing speed is a big issue, of course, with the digital filters. I found a very interesting test here from the Gansel group. They published a while ago. They took a Cortex M4 with a floating point unit. That's the same core processor I'm using for my experiments. They let it run at 120 megahertz. And they found that without floating point units, they needed about 180 to 320 nanoseconds per operation, adding operation. And with a floating point unit, And this Cortex M4 has a floating point unit on it. You can switch it on and switch it off. And if you switch it on, you only need 17 nanoseconds for adding operation, subtraction, and the multiplication. And the division only takes 83. Divisions usually take long, but yeah, we try to avoid divisions anyway. When it comes to computational efforts needed, you take a look at your bandwidth. If the sampling frequency is twice the bandwidth, your sampling period is 1 divided by the sampling frequency. And then you know, okay, that's the budget I have for doing all my computational calculations, my overhead, and all that has to be less than the sampling period. For instance, if we have a signal of 20 kilohertz that's of interest, then we need a sampling frequency of at least 2 times 20 kilohertz. Let's say we go for more 80 or 96, like I've been choosing then in my experiments. Then that gives you a 12.5 microseconds period. Within 12.5 microseconds, you have to be done with your filter calculations. And with 129 taps, and let's assume 4 cycles per multiplication and division, and this is already fast. I mean, you already probably use here a floating point unit with only 4 cycles. Then you would come up with a CPU speed of at least 40 megahertz. So some calculations like that you always have to perform. All right, and that's my implementation of a second order low pass and actually also a high pass filter. I'm using an STM32F4 discovery kit. That's an STM32F407 with 168 megahertz core speed CPU clock. And this microcontroller has an analog digital converter and a DA also on the chip. I think it is 16-bit maximum AD and the 12-bit DA, but I'm not using it. I'm using an external device, an external module, the PMOD I2S2, and this PMOD I2S2 has 2 Cyrus chips on them. One is a analog to digital converter and one is a digital to analog converter, and it has a stereo input, a stereo output, true 24-bit with a maximum 108 kilohertz sampling rate. And so this is a module that is performing very well for audio hi-fi data processing. And of course, the interface of this module is a digital interface. We have an I2S bus, and I can configure my STM32F4 discovery kit as having an I2S input and I2S output, and therefore the I2S bus here for the STM32F4 is in full duplex mode. So we can send and receive I2S audio data packages at the same time. The module pinout, you see there are a few pins for the digital to analog converter, a few pins for the analog to digital converter. Many of these clocks can be used in common. And so we have the output, the data stream out of the analog to digital converter. And we have then the digital to analog input data stream. And these are 2 pins. And then we have a master clock. The master clock is clocking the ADCs and the DAC, and typically that's 128 or 256 times the sampling frequency. In my case, that's 24.6 megahertz. So you have to be sure that you get 24.6 megahertz out of your GPIOs here. You have to be able to drive them, and then probably don't have too long wires. That's already a pretty nice transmitter. And then you have a serial clock. The serial clock is clocking the data bits out, and 24 bits of true data is transported or is represented in a 32-bit data stream, which is 2 bytes. So you get your 24-bit stereo data in 2 bytes, and so it's 2 times these 2 bytes times the sampling frequency. So I have a 6.2 almost megahertz sampling clock, serial clock, And then we also have to get the information, are we talking to the left channel or the right channel? Do we get data from left or right? And so this left-right clock is also running, of course, at the sampling frequency. You can find my code on the GitHub, and many thanks to another guy from YouTube with his channel, Yet Another Electronics Channel, I think it's called. And I've learned a lot from him. He made a lot of fun experiments on that topic. He's also using this module. So thanks to you. So we have already talked quite a bit about this 24-bit resolution that we have on these ADCs and DACs. And this 24-bit resolution is wrapped up in a 32-bit integer. And this integer is going to be reconstructed of two words with 16 bits. And the higher word is going to be transferred first, and then the lower word is going to follow right after that. And so you have to reconstruct out of two words this 32-bit integer. We use two circular buffers for the receive and the transmit. And the way these buffers work is that we first, for instance, receive the left 16-bit, the higher 16-bit, then the left lower 16-bit, then the right higher 16-bit and lower right 16-bit, and so on, 2 times. And we do it 2 times because we are going to use a direct memory channel. The DMA channel is transferring the input directly to the memory or transferring from the memory directly to the output, and without using the CPU core. So the CPU core is free for other stuff, for instance, free for calculating the filter, the actual filter. And what they provide us, that's very nice, in the circular buffer, they give us a half complete interrupt, and the DMA gives us also a complete interrupt. So that means when we are halfway through, if we have 8 words that we have here in this circular buffer, then after 4 words I get an interrupt telling me, hey, the first 4 words are ready for you to compute. And so I do the the filter computation on it, and I send the data out. And while I'm doing this, he keeps receiving the next 4. And when I'm done with the filter calculation of the first 4, I get the second interrupt telling me, hey, by the way, the buffer is now complete. And then I can go ahead and calculate then the second 4 words, and so on. That gives me a continuous stream on the output. So I don't have any pops and cracks and any noise on the output. I can keep continuously getting data, calculating, sending data, getting data, calculating, sending data, so we get a current stream. The IIR calculation itself is done very simply. It is just representing the formula we saw before from the IIR for a second order, 1-to-1. So you have a coefficient B0, multiply it with your input sample, take the coefficient B1, multiply it with the input sample from before, take B2 and take the input sample from even one more before, and subtract the coefficient times the result from last time, and with A2 the result from 2 times before this time. And so it's a straightforward representation of this formula. You could also use the SEMSYS library. SEMSYS is a library provided by ARM. They have a SEMSYS DSP library, and in this library you have all kind of mathematical tools available. Also filters, ARM FIR filter for floating point, you have IIR filters for floating point, you can have fixed point arithmetic filters, and so on. Also fast Fourier transformation, you find modules there. They also have a precompiled library that you can just link together in your development tool, and then just call the functions that you need. So these are the 2 filters we designed for the low pass and the high pass. I think the left channel, the left stereo channel, the left channel is the low pass and the right channel is the high pass. You see here 96,000 Hertz sampling frequency and a corner frequency of 1 kilohertz for the low pass and the high pass. Rather high stop band attenuation of 60 dB. And both are inverse Chebyshevs that I've been choosing here. And you see the filter performance here on the graph. And on the right side, you get the parameters. So you have the same calculation, the same formula for IIR that you use for high pass, low pass, but you have different coefficients. That's the only difference. So you have the A0, A1, A2, and B0, B1, and B2. And these IIR filters have always a A0 of 1. And don't get confused, sometimes A0, A and B is inversed. So double check with your implementation so you know exactly where to put these coefficients in your code. So let's move over to the bench then and take a look at how I implemented that. So STMicroelectronics is providing you with a nice integrated development environment, this STM32 CubeIDE. And in this CubeIDE, they have integrated CubeMX as a configuration manager for your microcontrollers. You see here, this is my STM32F407. And with this configuration tool, I can define each and every output. This is the input, is it an output? For instance, here, this GPIO pin PA1, it's a GPIO input. And I can change it to a GPIO output if I want to. So now it's an output, and you can configure your output. You can define if it has a pull up and pull down and what kind of speed you need on these output. I'm gonna change this back now to input. And you can do this for each and every pin of this chip, and you can select what kind of a functionality you need. Do you need AD, input, output? Do you have a USB functionality that you need, or that you don't need, a UART functionality, and so on and so on. And so you configure that in here, and then CubeMX is generating initialization code. And on top of this initialization code, within this initialization code, you can go ahead and start your application. And when you ever go back and see, oh, I need another pin as an input and an output, you always can go back, change that, and go back to your initialization code. And it's properly separated your user-defined code and initialization code. And so it's a very powerful, very nice tool. You're very fast setting up your microcontroller and get up and running. Also, the clock configuration is done for you, which is sometimes a pain in the butt with these sophisticated microcontrollers. And you have a visual configuration tool here available. I, for instance, use an 8 megahertz crystal, which is on the board, and go through the PLLs and generate 168 megahertz clock frequency, core clock, which is maximum here in this STM32F407. So what's really interesting here is not so much the inputs and the outputs. There are hardly any. Important is this I2S configuration, I2S, I squared S bus. And I think let's take a look at the parameters. What is important is you have a master mode, transmit, of course, then you have a data format of 24 bits in a 32-bit frame. And then this is my selected audio frequency. It's 96 kilohertz, the sampling rate. And after configuring this, you would have to also configure your DMA. And this DMA is configured in one stream to transmit data from the peripherals to the memory, and another stream from the memory to the peripheral. So we have two streams. And these streams are configured circular, not normal. Normal means you do it once and you transmit the data, and then the DMA waits for the next instruction. So what shall I do next? And he just sits there But what we want is a continuous stream of data coming into the microcontroller, going out of the microcontroller. So this is the circular mode. And I think that's mainly all that you have to configure. Of course, full duplex, because we want to send and transmit at the same time. And the interrupts are by default enabled. So we are all set. So let's take a look at the code. We start with some initializations for GPIO, DMA and I2S. This is provided by CubeMX. The user code starts from here. These are my variables I need for my program. These are float variables. And you see here the coefficients B0, B1, B2, A1, A2 for left and right. And you have two variables for the last inputs and two variables for the last outputs. And this is the circular receive and transmit buffer. And then we have here the actual filter calculation. We take an input sample as int, cast it to float, and then do the float calculation here, which is nothing else but the B0 coefficient times the input sample, plus the B1 times the input sample from before, plus B2 from the input sample from before, and then A1 times the last output, A2 times the last output before the last output. Then move the data one further, and then return the calculated filter result out. And then that gets transmitted through the DMA to the digital analog converter. And we do this for the left and the right channel, exactly the same. And when the circular buffer is half complete, we get the first four buffer values, 0, 1, 2, and 3. And so we have a complete left sample and a complete right sample ready. And then we do our filter calculations on top of them for the left and the right, and we just put it back into the transmit buffer. And we do the same thing for the complete callback, and that's it. And in the main, all we have to do is actually define the coefficients. And so the while loop, actually the while loop doesn't have anything to do, because it's all interrupt driven and the while loop is empty. It's doing nothing. However, for demonstration purposes, I set up in a while loop a switch over from a 1 kilohertz filter corner frequency to a 2 kilohertz filter corner frequency. And all we have to do to switch the corner frequency from 1 to 2 kilohertz is changing the filter coefficients. And that's what I'm doing here for demonstration purposes. I switch every 2 seconds from a 1 kilohertz low pass, high pass to a 2 kilohertz low pass and high pass. So this is the STM32F4 discovery kit. This is the PMOD module. We have the input coming from a SIGGIN, where the left and the right channel are combined together, so the same signal on left and right channel. And this is the output. The output gets probed, left and right channel again, left channel low pass, right channel a high pass filter. And here we have the SIGGIN. And with this SIGGIN, we can sweep from 100 Hz to 5 kHz. So let's take a look at the scope then. This is the output of the low pass filter. We start our sweep at 100 Hz and go all the way up to 5 kHz. The SIGGIN has an external output, a trigger output, and on this trigger output, this triggers off when the sweep starts, so we can nicely synchronize. And this is a linear sweep, and we can also go on a log sweep, and this looks more like a boat plot where you have constant attenuation or gain, and then you have your 40 dB per decade roll off of the low pass filter. And then we can also take a look at the high pass filter. On a both plot it looks like this. You see the blue is now the high pass overlaid, and I can switch back again to linear sweep, and then you see that around 1 kHz we have this roll off on both of these filters. These 1 kHz are not precisely, because this 96 kHz sampling frequency is not exactly generated. It's a little less, so you have errors here and there, but the principle can be shown. Now I'm sweeping manually through the low pass filter. We are now at 500 Hz. This is the output of the low pass. And when we go up in frequency, this is 700, 800, 900. And it starts rolling off here 1 kHz, 1.5 kHz, 2 kHz. So we see that the roll off starts at around 1 kHz. So we are happy with the performance of this filter. Now I'm sweeping from 100 Hz to 7 kHz, and I'm changing the filter coefficients every 2 seconds. I change from a 1 kHz low pass filter to a 2 kHz low pass filter. And you see here 2 kHz with a higher attenuation. And the same thing I'm going to do with the high pass filter. So the high pass changes as well from 1 kHz to 2 kHz. So you can do this on the fly. This is very, very nice. This is not something easy to do in analog filters. But in digital filters, you just change the coefficients and that's it.